Okay, I'm going to start. I'm John Derry with North Carolina CGIA, and I want to welcome everybody to this session entitled Modeling Trees with Deep Learning Using Aerial LiDAR and Photos. We have three speakers today. One is Vishnu Mahesh. Vishnu is a PhD candidate at the Center for Geospatial Analytics at North Carolina State University. His research focuses on modeling trees for solar energy potential estimation in urban contents. Our second speaker is Dr. Laura Tatioshan. Dr. Tatioshan is faculty in the Center for Geospatial Analytics at North Carolina State University. She's a computer scientist with research focus on using visualization, human-computer interaction, and natural language processing to explore geospatial data. And we have Dr. Purva Badin. She is at the Center for Geospatial Analytics Department of Parks, Recreation, and Tourism Management. And so go ahead, Vishnu, take it away.
Sure. Thanks for the introduction, John. Have you ever wished if there were an app that would help you park your vehicle in shade? Or how about an app that would help you plan a shady hike on a hot summer day? Or how about a tool that would automatically place 3D tree models in a scene for the entire extent of a city? The work I'm going to describe today could help make these goals a reality sometime in the near future. In this study, we aim to place realistic 3D models of trees over large study areas. Before we discuss how we plan to do this, let's discuss why do we need realistic 3D models of trees. You are probably familiar with 3D visualizations of cities as shown here. So these kind of visualizations will look better if we have realistic models of trees. So one of the most obvious application of realistic 3D models of trees is in those applications where realism matters the most. But are realistic 3D models only useful for realistic visualizations? Of course not. There are a lot of other applications where these realistic 3D models could come in handy. For example, shade analysis. Realistic 3D models of trees could better estimate shade over public surfaces such as streets or greenways or trails at any point in time. This would help the public to plan their recreational activities on hot summer days. Another example is viewshed analysis. A viewshed is basically an area that is visible from a viewpoint.
Hi, Vishnu. Sorry I'm interrupting, but the slides are not moving. Can you please check which slide you are in?
Okay.
Our screens haven't updated.
Oh, okay, okay.
We are still in the cover page. Okay, now we see the second image, second slide.
Okay, so yeah, so realistic 3D models are not only useful for realism or not only useful for applications where realism matters the most, they are useful for many other applications too, like shade analysis or viewshed analysis. And another interesting application is building energy modeling. Shades cast over building facades may either increase the energy demand or decrease the energy demand of buildings. For example, in summer, the shade cast by a tree over a building facade may help cool the building, thereby reducing the power consumption of the building. But in winter, the shade cast by the sun may block sun's warm rays from reaching the building, thereby increasing the power of consumption of the building to warm the building. So having realistic 3D models would help us model building energy demands. They can also locating sunniest locations for placing solar panels over a roof. The slides are not moving, just a second. Just hold on a second. There's some technical difficulty here. Can you see my slide moving?
No, we still see the slide with the three GIS modeling applications.
Maybe I'll close the screen and start again. Just a second.
Since we're paused, be sure to speak quite loud. It's the sound is a bit iffy.
Okay, cool. Okay, now can you see the slide here?
Yes, we see a new slide.
Okay, so let's talk about what's the current status of tools that model 3D trees. So this is a snapshot from a web scene. They actually look really good, but the problem is that they do not represent ground reality. For example, the oak tree or the tree that you see here is manually placed by a designer over there. They do not, sometimes it might be, in reality, it might be a oak or a maple tree over there, but the designer has chosen to place an oak tree over there. So this does not represent the ground reality at all. So since we have 3D tree models that do not represent the ground reality, we cannot do geospatial analysis on them. And also, since there is a human intervention required to assign 3D models to these locations, these techniques cannot be scaled over large areas. So as many of you may know, Esri has a library of 3D models of trees. They do have many models of trees belonging to various different species. But they are pre-configured 3D models. They are good for geospatial visualizations, but they cannot be used for geospatial analysis. Therefore, the objective of our research is to build a system that will locate realistic 3D models of trees based on ground information on a large scale. This would enable more precise geospatial analysis. Now, how do we create real-world 3D models? So there are two ways. One way is to use a terrestrial laser scanner. A terrestrial laser scanner is an instrument that shoots laser pulses. And depending on the time the laser pulse takes to reflect back from a point, we can calculate the distance to the point. This instrument shoots thousands of, or maybe hundreds of thousands of laser pulses per second. And the data that we get out of this instrument is a point cloud where the X, Y, and Z coordinates of each point are known. So this data is also known as LiDAR data. LiDAR stands for light detection and ranging. So the problem with this instrument is that this instrument is costly. So another cheap alternative is to use circumnavigational images of trees. There are a few photogrammetry softwares out there which can take in circumnavigational images of trees and create 3D models from them. And we don't even need any high resolution camera to do this job. Even a cell phone camera will do. So to create a 3D model of a tree, we need to have around 100 or maybe 80 to 100 images depending on the size of the tree. And we have to input these images into photogrammetry software. We are using Agiso Metasheet Professional, which is a proprietary software. Even though there are alternative open source softwares out there. And this tool will give us 3D models of trees. Now, we have talked about creating a 3D model of individual tree. Now, what about creating 3D models of thousands of trees of an entire city? For this, first we have to segment each tree from the aerial LiDAR data. By the way, aerial LiDAR data is publicly available for all the counties of NC. It is basically similar to terrestrial LiDAR data, except that this is captured from an aerial platform such as a UAV or aircraft. So once we have this individual segmented aerial LiDAR data, parallelly we would create 3D models of trees using structure from motion. and we will create a representative sample of trees, and we are only focusing on leafless trees in this study. And using a deep learning model, we will find the best corresponding match to our aerial LiDAR data and best corresponding match to our realistic 3D model from the aerial LiDAR data. And once we have the most corresponding model, we will use that particular model at the location of each individual tree in 3D visualization. This is how a 3D scene can be formed over large areas. Now, so this is the essence of the study. The accuracy of the results is highly dependent on the resolution of LiDAR data. If we have higher resolution LiDAR data, the accuracy will be better. Now let's discuss about the technical details. So as I have mentioned earlier, we will be using individual LiDAR. Sorry, we will using the LiDAR data of a study area, and then we will segment each tree from the data, and then we will use a deep learning model to match it to one of the structure motion models. In particular, we'll be using convolutional neural network. And those who are familiar with convolutional neural network know that we cannot directly use a 3D model as an input to a convolutional neural network or CNN. So we have to convert this into a 2D image before we can use it in CNN. So for this, we will apply a few voxel statistics over the 3D data, and voxel statistics will be selected so that the 3D characteristics of the 3D data are preserved as much as possible in the 2D data. And those of you are familiar with convolutional neural network know that a convolutional neural network cannot output a 3D model. It can output only a label. For example, in a CNN that can detect animals, the input is the image of an animal, and the output is the name of the animal, not the 3D model of the animal itself. So in a similar way, our model cannot output the 3D models of the trees directly. So we have to ask.
Vishnu,
Yes.
Can you turn your video off to see if it will help with the sound?
Just a second.
Your camera?
Yep.
Sorry.
Okay. So can you hear me now?
Yeah, but the audio is just a bit broken up. Just try to speak loudly and you know,
okay,
the best you can.
Okay. And so we have to assign a category label to each of the 3D models. And so the biggest question is, how do we train the deep learning model? So as, for example, in a deep learning model to detect an animal, we have to give a lot of inputs of image and label pairs. For example, here in this image, we are giving inputs as image of a cat and the corresponding label. Similarly, our deep learning model has to be trained too. For this, we will be using the 2D images and corresponding category labels. But the interesting question is that, how do we find the category of the 2D image? If we look at the cat, we can say it is a cat. But if you look at the voxelized 2D image, how do we know the category? For this, we will be using Google Street View images. So we will individually segment each tree for training, and then we will also collect the Google Street View images of the tree. And depending on the form, the height, the canopy diameter, and there are a lot of criteria, we will categorize this aerial LiDAR data into a category. So this is how we will train the deep learning model. And this is the most important part of our model actually. And the plan that I have described here is part of an ongoing research. We have begun exploring a number of components. We have started creating 3D models of trees using structure from motion. And we have also started on deep learning or the convolutional neural network. And we have also started on segmenting the individual trees by testing a couple of algorithms. And we are planning to use Charlotte as our study area because Charlotte has a higher resolution LiDAR data. It has a QL1 data which has at least 8 points per square meter, and even Charlotte has even more points than that. To summarize, we will initially create realistic 3D models of trees with the help of circumnavigational images. And then using deep learning, we will find the corresponding match for each tree in the aerial LiDAR data of a large steady area to one of our realistic 3D models. The 3D scenes made with these model trees could be then used for shade analysis over streets or in building energy modeling softwares or tools. I just read through my presentation. That's all from my side. If you have any questions, please let me know. Thank you.
That was a great presentation. I'm sorry about the audio.
I don't know what happened there, but was the audio bad all throughout, or is it?
Mostly throughout. I don't. It could be your mic.
Okay.
But if anybody has any questions, please feel free to put them in the chat.
I see some questions are coming in.
Yeah.
Oops, my.
Would you like me to read them? I'll start with it. The first question is, I apologize if you answered this, the audio coming through is choppy, but you use the 2D version of the tree metrics such as tree height, canopy width, coupled with the LiDAR data to predict the tree species in the urban landscape. Have you used this in a forested landscape?
Yeah, that's a great question. I realized that in forest, the trees will be standing very next to each other, and individually segment them will be a tough task. But yes, this can be done in forested landscapes too, but the accuracy won't be as good as detecting individual trees. But definitely this can be done through done for forested landscapes too. That's a great question.
The challenge there would be we're using Google Street View image as well, so we'd have to adjust for how we're looking for those, right?
Okay.
Yeah, yeah.
But there's not a street through the forest.
Yeah.
Yeah. Here's another question. What is the percentage of work for training model?
Yeah, that's a very good question. It's the, I mean, that's the major chunk of this work, like training the deep learning model, because we need to collect the Google Street View images. We need to segment the images and then start the training. And one other interesting fact is that we will not have enough input training samples just from the Google Street View images. So we will have to rotate our training samples by around 2 degrees or something like that, so that we have 180 images per tree. So we have to have some tweak there to have enough number of input samples. So in training is the hardest part, and we are looking forward to that. We haven't started that yet, but hopefully we will have it soon.
But you have done some exploration, you had some pilot work with deep learning models, so it's not totally unknown territory, but trying to apply to this content is what is next.
Okay, another question. This is such an innovative study and practical too. Daydreaming how we could try to use this for fixed wireless broadband access work. wireless propagation models, which essentially is viewshed line of sight analysis.
Yes, unless the trees that are near these, I mean, this can be used further down the lane, not immediately, because I realized that the trees that are near these facilities might be very deep in the forest, or it might not be not something that you usually see in urban areas, because Google Street View images are taken from urban areas. So the trees that are over these areas might not be, the deep learning might not catch them up pretty quickly. So yes, that can be trained, but that's further down the line. We have to manually take the images for training them. Yes, but that can be added on to this deep learning model.
The next question, I may have missed it because of the audio, but is the LiDAR data sourced from publicly available data, or are you collecting it over specific areas of interest?
Yes, the data is publicly available online. I am downloading it from Spatial Data Download. So you can Google it and find the website. So yeah, I am specifically downloading area of Charlotte from Spatial Data Download.
I apologize if I missed this. Where are you running your deep learning trainings, and with what software?
So we have not decided on, we have not started upon that. So we will be using our HPC over at NC State University, or if it's not so complicated, maybe we will run on our personal machine. But we have not reached that heavy duty part yet. And we hope that we can solve it within our HPC over here.
And what is the software?
So we will be using programming languages such as Python, and maybe, I know ArcGIS has some deep learning models out there, but we will have to go for customized deep learning models. So we will stick with Python and the corresponding libraries.
Have you looked at research conducted where LiDAR has been used to evaluate chemical composition to then determine the species?
No, we have not done that, but this can be applied in tandem with hyperspectral images. I know hyperspectral images are capable of detecting, because it has a more number of bands, it's capable of detecting the species of trees. So yeah, this can be included, or I don't know if LiDAR can detect the chemical composition, but chemical composition or the species can be determined by hyperspectral images, and this can be combined with the LiDAR data to accurately detect the species. But we are not doing that, but that's something that is doable.
And Dr. Tatioshin has asked the questioner, do you have any references to share?
No, I was responding to Byron about
okay.
the chemical composition with LiDAR, asking if he has some references he could share about that.
Okay. May have missed this. Are the input images used for the model to collect, for all collected from warmer months? Imagine it would be difficult to get accurate representation of deciduous trees in the winter, etc.
I'm sorry, could you repeat that question again?
Okay, may have missed this. Are the input images used for the model all collected from warmer months? Okay, are the images all collected from warmer months? Imagine it would be difficult to get an accurate representation of deciduous trees in the winter.
I think the question might be other way, like it might be difficult to get deciduous trees in summer. So yeah, so we have collected deciduous trees the samples of deciduous trees, especially for the structure from motion models. We are collecting the images in winter. And the Google Street View images, if you are asking about Google Street View images, it has a combination of winter images and summer images. So we cannot say we will get a fixed number of wintertime images. It is dependent on the API, Google Street View API. So yeah, but we have seen that we get a lot of wintertime imagery as well.
Maybe I can add to that question, to that answer, Vishnu. The original idea that actually prompted this project was looking into energy potential estimation, particularly in winter months where actually leaves fall off and the trees do not have leaves. So we would like to actually being able to predict or estimate the energy potential or sun penetration that goes through the branches. That's where we are focusing actually on imagery taken in specifically in winter months where deciduous trees do not have leaves.
There was a question that, I don't know if it was a question or just a statement. Lots of bamboo in our area. I don't.
Okay.
Yeah, I was actually curious about that. I was going to ask Evan, what were you getting at with that?
Yeah.
Yeah, so I think bamboos are a lot of stands that stand next to each other, very close to each other. So yeah, I realize it will be very difficult to individually segment these bamboos. But if the resolution of the LiDAR data is high enough, then we can individually segment them. That's possible. But the constraint is the resolution of the LiDAR data. And Charlotte has around 25 points per square meter. So we are hopeful that we will get a good representation.
The species determination can be expanded upon to ascertain future shade potential based on average growth patterns of the species. I think maybe you're all having a conversation currently with Byron, right? Looks like with that question.
Kind of wish the audience had microphone.
Yeah, I know. And then Byron asked, do not know, or said, do not know the exact details, but I know Mike Mandrins of Appalachian State University was looking into similar concepts.
Yeah, that was in response to the question about the chemical composition, if he knew any references to that.
Yeah, okay. And Evan has replied, that's what I was getting at, thanks. So you have answered Evan's question. So, there's a lot of interesting comments, posts on the chat. So that was a great presentation.
Are there folks in the audience who are doing deep learning projects that we'd like to get your contact information, and it'd be good to know.
Okay. Well, we don't have any more comments coming in. It's about the top of the hour. So thank you all for coming.